you can have no two electrons in the same quantum state. This is known as the Pauli exclusion principle, and it basically comes as a result of thinking of particles as being completely indistinguishable at the quantum level, which is not the case classically. Particles such as electrons, or any other fermions for that matter, are not able to be in the same quantum state. This actually produces all of chemistry, because if you think about it, the entire structure of the atom all revolves around quantum numbers and electrons occupying discrete energy levels. And which discrete energy levels those electrons are in basically governs how electrons from one atom interact with electrons from another atom. Now in this video, we're not going to be talking so much about atoms, but we are going to be taking a deep dive into the world of fermions, and we are going to be looking at their dynamics and how the Fermi distribution, which is here, is going to be used to uncover all sorts of weird effects that are going on in the world of fermions. Specifically, we're going to be having a look at how this applies to metals, because of course metals are a sea of fermions. Of course they have a lattice of positively charged atoms, but they are a sea of whizzing electrons, and we are going to be unpacking what's going on in that regime. Without further ado, let's head into it. So like I said, fermions can only occupy discrete different states, and for example, I'm going to consider a very simple example. We're going to have two electrons, and they can either be in the spin up state or they can be in the spin down state right there. And so those are the two states of the electron spin in this particular configuration. They can either be spin up or spin down. And the key thing is, in a given system, you can never have two electrons that are both spin up. One has to be a different one from another. Of course, you can have two spin up electrons, but you have to treat that as being in a different system, such as to follow the Pauli exclusion principle. So let's go ahead and start with our average occupation formula for the Fermi distribution, which is 1 over e to the epsilon minus mu over kBt. And for the Fermi distribution, it's +1. So for the Bose distribution, you've got to be a little bit careful. This sign is a minus. In the Fermi distribution, it is a plus sign. And it might not look like much, but oh boy, can that plus sign make a whole lot of difference. What we're actually going to do is actually similar to what we did in the video on Bose-Einstein condensation. We are going to sum over all of these average occupancies to calculate the total number of fermions in the system. And we're going to do this as a function of chemical potential. So of course, chemical potential is the property determined by the system itself. If we have our sort of box of gas, I think we're a little more comfy with the idea of the box of gas having a well-defined temperature. Box of gas has got a temperature T. In this case, we are considering the case where particles are able to flow in and out of the box. And so for that, we need to have a chemical potential mu, which basically determines the capability for particles to be able to do that. So it's very similar to temperature in that it basically is like showing the capability for particles to flow in or out. So we want to get the number of particles at a temperature at a chemical potential. So to get n, capital N now, the total number of particles, we are going to be summing over all the states, nk, or just k. I haven't really been notating this very well, but basically when I do a sum like this, I'm normally summing up over all the states. So we're going to go e to the epsilon minus mu over kBt plus 1. And just like we did for the boson case, we're going to go from a discrete sum to an integral over density of states from 0 to infinity. Density of states multiplied by the Fermi distribution, e minus mu over kBt plus 1. If you guys are not comfy with this step, I do explain it a little bit more in the Bose-Einstein condensate video. But basically what I'm doing is I'm doing an integral over energies to calculate the total number of states, n, but I'm going over energies and I'm multiplying it in each case by the density of states in order to account for the fact that you can have multiple states at the same energy. But of course we have statistical fluctuations now, which are determined by sort of mu and t right there, and that's what the Fermi distribution is accounting for. What we're going to firstly do, because this is actually a really hard integral to solve, we're going to firstly consider the case where the temperature is absolute zero. So normally temperature can't actually get to absolute zero, but in this case, it's actually going to make the maths a little bit easier, which I know sounds a bit like a physicist cop-out. You can use the result that you get at temperature being equal to zero to go on to derive stuff that's basically a bit more applicable day to day. But yeah, you do have to go through this slight detour of temperature being equal to zero, which in actuality you can't quite get there, but you can get really damn close. So I want to ask the question, what's going to happen to this part of the integral right here, the Fermi distribution, as the temperature approaches zero? Well, you're actually going to have two different cases for what's going to happen. Of course, if we plot out, the easiest thing to do is to plot out the Fermi distribution. And as I said, it was something a little bit like this. This is just for a temperature technically above zero, but we can analyze sort of what's going to happen generally for a real temperature, and then see what happens as it goes to zero. So this is the average state occupancy, and this is epsilon right here. So, and I said that this kind of midpoint right here, this point right here, was the chemical potential mu right there. So let's have a look at the case where epsilon is greater than the chemical potential. So the energy of the particle state, the state particle energy, is greater than the chemical potential. So what are we going to have in this exponential right here? Well, if epsilon minus mu is a positive number, so let's just write that out, epsilon minus mu over kBt, and we are having a look at the case where t goes to zero and epsilon is greater than mu. So we're going to have a positive number right here in the numerator because epsilon's greater than mu. And as t goes to zero, when the denominator goes to zero, then this whole term is going to start getting really, really big. So if you think about like dividing by a really small number, the overall term is going to become really, really big. So this is actually going to tend toward infinity. For very low temperatures very close to absolute zero, you're going to get this whole term tending towards infinity. And so what happens to e to the infinity? Well, e to the infinity is going to also get really, really big. I mean, if infinity's big, then e to the infinity is going to be really big. So, like, unimaginably big. And comparing it with this +1 right here, it's not going to matter at all. So we might as well just eliminate this +1. So e to the infinity +1 is basically the same as e to the infinity, like proportionally. So we can just kind of ignore this +1 right there. And of course it's being inverted, it's 1 over e to the infinity. So 1 over e to the infinity is equal to e to the minus infinity. And e to the minus a really, really large number just basically is 0. So as you can see, what's going to happen for a small temperature is that in any case, in every single case where epsilon is greater than mu, then this distribution will just always be 0. So it doesn't even have to be that much bigger than mu. Like, if in any part of this portion of the graph right here, as the temperature starts lowering really, really close to absolute 0, then this average state occupancy will just be 0, because this is by far the domineering term. The e to the minus infinity is just going to basically kill any state availability for low temperatures. So let's go ahead and draw in what we think our graph is going to be like for temperature going very, very cold. And I think we should do it in blue just because blue is typically a cold color, although in stars it's not. But Anyway, we're going to do it in blue. So here we have what we think is going to be the case for epsilon being greater than mu. So what about the other case? So as t tends towards 0, but for epsilon being less than the chemical potential. Well, in this case, you're going to have epsilon minus mu over kBt. This time you've got epsilon minus mu, but of course epsilon is less than mu. So this whole term is going to be negative. And so therefore, if you divide it by this, then that whole fraction is going to be negative. And so when you get very, very large values, very small values for temperature, you're actually going to tend towards minus infinity. Rather than infinity, you're going to go towards minus infinity because this whole term is negative. So epsilon minus mu over kBt goes towards minus infinity. So what does e to the minus infinity do? Well, e to the minus infinity is, just like we said before, basically 0. So e to the minus infinity plus 1 is basically 1. So in this case, 1 is the domineering term. That's going to be far more prominent. Of course, that's the denominator of all this. Of course, we're taking 1 over, but of course 1 over 1 is 1. So this whole term right here, in the case of epsilon being less than mu, is just going to be 1. And so if we draw that in right here, so this was where 1 was on the graph before, you're going to end up with this function, and this is called a top hat function or a heaviside step function as its technical name. But all this function is really saying is that below mu, the chemical potential, this critical chemical potential, which actually has a name, then all the states are occupied. There is a 100% probability that all the states are occupied. But then above this value, none of the states are occupied. And the key thing is there's no kind of fluctuation. Obviously, when there's no temperature, there's no movement of the electrons. They're not going to move between states. So they're all just going to be like down in the bottom, just kind of stuck. So that's basically what's happening to this distribution at very low temperatures. You have a constant value in this part of the graph of 1, and then suddenly it just cuts off to 0. So another way to maybe like draw this out is by having a look at like the dispersion curve, and then thinking about how the electrons are going to fill up these states. So they're all going to fill up the states one by one, increasing energy, but there's going to be some kind of a cutoff point right here. And I'll go on to talk about this cutoff point in just a second, and above which you have absolutely no probability that the electrons are going to be in any of the states sort of here above this cutoff point on the dispersion curve. So how do we calculate this cutoff point right here? Well, we're actually going to take this integral right here, and given what we know, we can now actually kind of simplify it to some extent. And so let's go ahead and rewrite it, and let's see what we can kind of do. So n, we're considering for the t equals 0 case, the number of particles to total number of particles is going to be an integral over energies, which is kind of our approach right here. Now, let's go ahead and think about what the limits are. So what we said was we're going to have all the states being fully occupied up to this kind of cutoff right here. So we're going to start at 0 energy, and let's go ahead and call this cutoff frequency, this cutoff chemical potential mu dash just for now. We're going to have our density of states right here in the integral as before. But this term right here, this is just 1 for all this part of the graph. So we don't need to bother writing it out or doing any kind of fancy integration with this term here, because it's probably not a very easy looking integral. So we just can write 1 right there. And this is going to be integrated over epsilon, which is the energy. So now all we have to do is substitute in our density of states, which we're going to do for a 3D system. Of course, you can actually do this for a 2D or a 1D system, or basically any system which has a different dispersion relation. But we're going to go ahead and do it for 3D massive particles. So this is between 0 and mu dash, this cutoff chemical potential. And the density of states, I said in previous videos, is going to be proportional to square root of epsilon. So that's for 3D particles. What we wrote was, we just factored out all the constants apart from volume into this C term right here. And then we just included the volumes separately in case we talk about densities and we need to divide by volume, then we can just do that. And then the important thing is it's proportional to the square root of energy. So let's go ahead and sub that in, CV root epsilon, d epsilon. And this is a pretty straightforward integral. We're just integrating epsilon to the half. So the integral of epsilon to the half is just, you add 1 to the power and then divide the coefficient by the power in this case. So we are going to get, add 1 to the power 3 over 2, epsilon to the 3 over 2, and then multiplied by 1 over that, which is 2/3. And yeah, okay, fine, I'll just put a plus C in there for you integration pedants out there, because I know I'm going to get a comment on that. So let's go ahead and do that for this. So we're going to get CV, and it's going to be 2/3 multiplied by epsilon to the 3 over 2. Now we don't actually have to worry about this plus C because we have limits, which is a lot easier. And this is integrated between 0 and the cutoff chemical potential. And then this is just going to simply reduce to 2/3 CV times mu dash to the 3 over 2. So there we go. We have our relationship between this cutoff energy and the number of particles. And now I can finally reveal what this cutoff energy is called. This is called the Fermi energy right here. So mu dash is got a special name. It is known as the Fermi energy, and it is defined as the energy of the topmost filled state of a system of fermions at 0 Kelvin, which is exactly what we see in the graph right here. Here's our graph for 0 Kelvin. It's the energy of the topmost filled electron state. And so anything up to the Fermi energy is going to be completely occupied, and anything above the Fermi energy at 0 Kelvin, this is not true generally, but this is true of 0 Kelvin, anything above that energy is going to be completely unoccupied, and so there are going to be no states filled at all. So you can rearrange this formula quite easily. So we're just going to say that mu dash equals the Fermi energy, which we normally give this symbol EF. And we're just going to go ahead and quickly rearrange this to get it in terms of the Fermi energy. So the Fermi energy is just EF equals 3C over 2 to the power of 2/3, which of course you can substitute in C. But the key thing is about the Fermi energy is that it has a relation, once you rearrange it, to the density, N over V, the particle density. So if we define N over V as a density, then we can see how the energy, the Fermi energy, is pretty much determined by the particle density, the density of the metal lattice. So you have your metal lattice right here. Of course, you're going to have a certain number of electrons sort of in this C, but each metal is going to donate the same number of electrons. So the lattice density will determine the electron density. So the number of donated electrons that each atom has to the electron C is going to determine the Fermi energy, because that determines the density, which then determines the Fermi energy right there. So the key point right here is that the Fermi energy generally is not the same as the chemical potential. Now, I thought they were the same for a while because I wasn't really quite sure what the chemical potential is. It is a bit of an elusive concept, but yeah, basically make sure that the Fermi energy and the chemical potential are two different things. The other thing to mention is that the chemical potential is a really clever quantity almost. You can kind of think of it a little bit like a thermostat in this case, because if you think about the case where we have a certain number of particles in the box, which is kind of the more common example. You've got a certain number of particles in a box and you change the temperature. This kind of appears to violate what we've kind of derived because, of course, the number of particles is a function of temperature. But that's where chemical potential comes in. The chemical potential will automatically adjust itself so as to conserve the number of particles. So if temperature adjusts, the chemical potential will adjust to compensate, which is really, really clever. It's kind of like a thermostat. So you can think of it a little bit like that as well. So now we're going to consider what's going to happen at small temperatures. Now, this is a bit of a lengthy derivation, and this is requiring a lot of careful maths and stuff. So you can skip ahead to this time right here if you want to just get to the end result and see what the point of this is. But this derivation right here is here for if you want to know how this is derived, because I know some people really like to know how things are derived. So what we're going to do now is we are going to calculate the number of particles as a function of temperature and chemical potential right here. Now, this might seem a little bit pointless at first, but actually if you do this, then you actually can derive some quite useful phenomena such as things like heat capacity and energy. Calculations like this are very useful in semiconductor physics, so this is not a pointless calculation. Now, I've mentioned this is at small temperatures, and I need to be a little bit more formal about that. Now, I defined, of course, the Fermi energy, but actually Fermi has a lot of quantities related to him. You actually have the Fermi momentum, the Fermi wave vector. Basically, the one I'm interested in is defining the Fermi temperature, which is just written like this. Fermi temperature is literally the Fermi energy divided by the Boltzmann constant. So it's like a sort of temperature reference point, just from the Fermi energy right here. And when I say small temperatures, what I'm actually meaning is that the temperature is much, much less than the Fermi temperature right here. Now, this might seem like one of these things where you can only see these effects at absolute zero. But actually, most metals, even at room temperature, behave in this way. So this is actually kind of useful to derive, even for things at room temperature, because the Fermi temperature is actually around 10 to the 5 Kelvin, which means that even at room temperature, but in the case of fermions, you can actually get these, sort of quantum effects. You don't know it, of course, just by looking at a slab of metal. You don't think it's exhibiting quantum effects. Fermions within the metal are in fact highly degenerate and are actually basically governed in this regime by the Pauli exclusion principle, and things like the Fermi energy are important. So let's go ahead and firstly write out our integral that we start off with as the number of particles is equal to the integral. Now we're going to be going all the way throughout all possible energies. So we're not just going up to the Fermi energy, we're going to go throughout the entire range of energies. Multiply the density of states right here, and going to multiply that by our Fermi-Dirac distribution, plus 1 integrated over epsilon. So before I do any more, I'm going to now think about what I'm actually going to be calculating, because as it stands at the moment, this integral is not easy to do. So firstly, I'm just going to plot out a couple of graphs actually. The first one is going to be the graph of the density of states, which we do actually know. We know what this is, graph of density of states against energy, and we know it goes something like a square root function. So we're not really too ambiguous about that. And the other one, of course, is this term right here, is the Fermi distribution. So this we said at absolute zero was a step function, so it just suddenly cut off at the Fermi energy and then was fully occupied and then cut off at the Fermi energy. But now we're no longer at t equals 0. We're actually we're still at small temperatures, but we're no longer at t equals 0. So the graph is actually going to look similar, but it's gonna be slightly kind of smeared out at this kind of part of the graph right here. Incidentally, this window is basically KBT right there, this like a sort of energy window in which the smearing happens. but that's kind of not important, but just to give you a reference for sort of how much kind of the distribution sort of smears itself out. What I'm now going to try and do is I'm now going to try and plot the product of these two graphs, which is kind of what we want right here. We want to get the product. The easiest thing to do is kind of start plotting the density of states as it is, because of course it's just going to be multiplied by 1. But then as we get to the Fermi energy, this smearing comes in right here. And so we're going to get a graph that looks a bit like this. So this is the product of the density of states times the average occupancy. And it's going to be the density of states graph, but kind of smeared out a little bit because of this graph right here. I'll just plot it just to be clear. I'll plot what it looks like when there is no smearing and it's at the absolute 0. You're going to get just the density of states graph because it's just being multiplied by 1. And then as soon as you hit the Fermi energy, then you're going to get absolutely no states at all right there. So this red curve is the t equals 0. I know it's not really the right color, but this white curve is a more general example at small temperatures. So this is t greater than 0, and you can see the smearing effect has occurred. What we're going to now do is we're now going to really look at this graph, and using kind of our knowledge of how to calculate integrals and sort of what integrals actually are, like graphically, we are going to try and calculate the area under this curve, this white curve right here, which is of course n, our total number of particles, at a certain temperature and chemical potential. So what I'm now going to do is I'm going to redraw this graph right here, but enlarge it so we can really see what we're doing. I'm firstly going to draw the graph that is what we want to evaluate, which is this kind of distribution where at temperatures that are greater than absolute 0, but are less than the Fermi temperature. And I'm now going to draw the t equals 0 curve, which is of course exactly the same as the density of states curve, up to the Fermi energy, at which point it just kind of hits 0 and is 0 thereafter. So we can see this kind of smearing effect occurring. So what I'm going to do is I'm going to divide the areas up of these two curves into different regions. And that is how we're going to be evaluating the total area under the white curve. So the first region we're going to consider is the area, which is going to be this red shaded region right here. It's going to be the total area under the blue curve. Now, this should be the most straightforward to evaluate. We've actually already evaluated this. This was the total number of particles in the system at t equals 0. So that's obviously not going to change. So what is going to change when we increase the temperature? Well, obviously you can see that the difference between the area under the blue curve and the white curve are kind of these two sort of regions right here. I'm now going to draw the next region. I'm going to draw this in yellow. So there's going to be this region here. Now this region is of course under the blue curve, but is not under the white curve. So to get the area under the white curve, we're going to get the area of the blue curve and then subtract whatever's in that region right there, that kind of yellow region, or that's slightly orange because it's overlapped with the red region. So we're going to subtract that area off. But if we have a look down here, we can see that there is more area that has been obtained from increasing the temperature. And this area, of course, wasn't here before. So we're actually going to add on this part of the graph right here. So we're going to start off by doing what we did before, t equals 0, evaluating the integral between 0 and mu. And then we're going to just subtract this part right here because it's not underneath the white curve. And we're going to add on this part right here, which is underneath the white curve, which wasn't there before. So now we just need to express all that in terms of integrals. There's going to be 3 terms, one for each kind of operation, if you like. I'm going to subdivide them into 1, 2, and 3. And so we are going to find that the total number of particles as a function of the temperature and the chemical potential is equal to the total number of particles in region 1, which is the red region, which includes this bit right here. That's still shaded in red. And we're going to subtract everything that's in this region right here, which is the orange region or the yellow region, but then when it combined with the red region, it would turn into the orange region. So that's going to be sort of N2. I'm going to call that just that section right there. And then we're going to add on everything above the chemical potential mu right here, which is going to be N3. So that's kind of our approach. Now let's go ahead and write in these integrals right here. So N1, we kind of knew what that was. That was just the integral between naught and it was the Fermi energy before, but now we're evaluating at any chemical potential. And of course, this chemical potential will generally change as a function of temperature for a given particle number. So it's going to be the integral between 0 and mu. And so inside the integral, we're going to have the density of states, rho. And of course, for t equals 0, under this blue curve right here, this is t equals 0, the Fermi distribution is just going to be 1. So like we said, that's the same integral that we kind of did before, except we're not evaluating between naught and Fermi energy. We're now just doing it between any general chemical potential. So that bit's quite easy. What about this next part right here, N2? What's that going to be? Well, N2 is a little bit more complicated in that we can kind of consider this region right here to be the kind of subtraction of everything under the blue curve minus everything under the white curve. But instead of being between any limit, we're just now going to consider this part. It only goes up to the chemical potential mu. So we can again perform the evaluation between naught and mu times the density of states. Now what are we going to get here? Well, we're subtracting the blue curve, which is of course just going to be sort of 1. The Fermi distribution is 1, minus, and I better put a bracket around here. So that's going to be integrated over epsilon. So that's the first bit. Minus, again, the integral between naught and mu, just the bit that is going up to mu, but this time not under the condition that the temperature is 0. So we're going to get density of states, and we're going to multiply that this time by the Fermi distribution, e to the epsilon minus mu over kBt d epsilon. So this is actually going to simplify a bit because of course we have two integrals being integrated under the same limits, and both include the density of states, so we can factor out the density of states. And so we can then just kind of shorten this to density of states and 1 minus all this right here. 1 minus the Fermi distribution, all that integrated over epsilon. So that was kind of the hard bit. So that required a little bit of thinking for sure to just really consider what this region is right here. And it's the subtraction of this whole blue curve minus this area that's just in red right there. And so we're subtracting this away from the blue curve to get this red region right here, which is of course terms 1 and 2. And now for our final part, we're going to add on the integral. Now in this case, we're actually going to be above mu. We're considering what's going to be the area under the curve above the chemical potential. And the upper limit is going to be infinity right there, because of course potentially it's going to go up to infinity. Of course you can see at large energies there's not going to be very many particles, but that is going to be the upper limit. And what are we integrating? Well, this is just simply the area under the white curve right here, because there's nothing under the blue curve. We're going to get no contribution, so we're just simply doing the density of states multiplied by the Fermi distribution. And that's going to be integrated with respect to epsilon. And there we go, that is our sum right there. Now, if we look at these three terms, we can see that this term right here is going to be by far the most dominant term. This is going to be very big in comparison to all the other terms, this term right here and this term right here, particularly at small temperatures, because we're not going to see huge amounts of smearing going on from the increased temperature. So let's go ahead and evaluate these integrals. Now, this is going to be very maths heavy, So feel free to skip ahead if you just want to kind of know the end result. But we're going to go through this and hopefully try and not make a mistake and try and evaluate the total number of particles in this Fermi gas. So the density of states right here, we can just simply substitute in, is CV. So we're going to get the integral again between naught and mu. CV, where C is just all those constants, multiplied by the square root of epsilon. And that's just simply going to be integrated with respect to epsilon. So that's fine. So we're going to get pretty much what we had before. The integral of a square root is just 2/3 whatever's under the square root to the 3/2 evaluated between the two limits. So it's going to be 2/3 times CV epsilon to the 3/2 evaluated between 0 and mu right there. And we're going to get nothing at the 0 limit, so we might as well just swap out the epsilon with mu to the 3/2. So that's the most dominant term. And as you can see right here, this is just purely temperature independent. But of course, the temperature dependence is going to come from these two terms right here. So here comes the difficult bit right here. Now we need to try and simplify this integral right here, because right now we cannot really integrate it. And so how are we going to do that? Well, let's go and just take this part out right here. And let's go ahead and see if we can write this in a form that makes it a little bit more easy to deal with. Or more specifically, makes it a little bit more like this integral right here. That's kind of what we're going to try and do. So let's go ahead and instead of writing 1 minus this, we are going to change this 1. We're going to combine the fraction, these two separate terms, into a single term under a single fraction. And from this 1, we're going to multiply both the numerator and denominator by this right here. This is the one and the same as e to the epsilon minus mu over kBt plus 1 over e to the epsilon minus mu over kBt plus 1. So that's just our 1 term. We've just written 1 yet again. We're going to subtract 1 over e to the epsilon minus mu over kBt plus 1. So a bit of a mathematical trick there, expressing 1 as this right here. But hopefully if you guys have done some sort of algebra classes before, then hopefully you'll have seen that kind of thing done before and it shouldn't be too mysterious. And then we can kind of clearly see that this is just going to become the plus 1 and the minus 1 are just going to cancel out. We're going to get e to the epsilon minus mu over kBt in the numerator, and that's all going to be divided by e to the epsilon minus mu over kBt plus 1. Now we can notice that there is in fact a minus sign out the front right here. And just to change that into a plus sign, just to make our lives a little bit easier, we can absorb this minus sign into this right here. So just multiplying this whole fraction by minus 1, put the minus out the front, which is going to be sort of minus e to the epsilon minus mu over kBt divided by e to the epsilon minus mu over kBt plus 1. So that's not quite equal, that's multiplied by minus 1. That's what we're doing just because we have this minus sign at the front. And just simplifying that, we are going to get minus 1 over 1 plus e to the minus epsilon minus mu over kBt. The integral, just this term right here, n2, we can now express this instead of the way it was previously written. This is now minus the integral between 0 and mu, rho of epsilon, times 1 over 1 plus e to the minus epsilon minus mu over kBt. So I'm now going to rescale this integral by making the substitution of x is equal to epsilon minus mu over kBt. We did this in a video before. It's basically to try and get the integral in terms of purely something dimensionless, So we can kind of factor out all the constants at the front and just get a purely numerical integral right there. If we make that substitution, we can rearrange this for epsilon, which is a little bit more handy for what we want. And that's going to be mu plus kbt times x right here. And then when we take a derivative, d epsilon is equal to kbt times dx right there. So that's fine. So we've done a similar thing to this before, and now we're just going to go and resubstitute all this stuff back into the integral and adjust the limits, because the limits are going to change when we make these kinds of substitutions. So n2 is going to be equal to minus the integral. When epsilon is 0, we're going to get x is equal to, when that term's 0, that's just going to be minus mu divided by kbt, right there. That's our lower limit. So our lower limit has now changed. And the upper limit, when epsilon is equal to mu, then what is x? Well, you can see that from this equation, when you substitute in epsilon is equal to mu, you're going to get a mu minus mu, which is just 0 right there. So the top limit right there is now 0. Now, we are, of course, writing everything here in terms of x. So our density of states, rather than being a function of epsilon, we actually rewrite this as mu plus kbtx. So we've literally just swapped out epsilon, but for kbtx, and put it in there. So that's kind of what I've done right there. And of course, the reason why we've done this is to get this Fermi distribution looking a little nicer. So we're going to simply get 1 over 1 plus e to the minus x now, using the substitution. And as for d epsilon, well, we're going to get a factor of kbt, just like we've seen before. So we'll bring that out the front. And so we're going to get kbt out front, and there's going to be dx right there. Now for this next step, it might seem a little bit weird, because it might seem like I'm doing something somewhat illegal right here. But what I'm going to do is I'm going to make this transform of x going to minus x. Now, you might think that's a very invalid transform, which normally you'd be right, that would not make any sense to make that kind of transform. However, of course, it doesn't really matter what variable we are integrating over, as long as we're consistent with it. Just as long as we kind of do the same thing to all the terms in the integral, so as long as we perform the same operation, the integral won't actually change itself, its value out the front, which is kind of what we're interested in. It's kind of a bit like what we do up here, except a little maybe shiftier, just because it kind of doesn't look really as good. So we're gonna, every time we see an x, replace it with a minus x. And what this is going to do is it's going to make the integral look a lot more similar to the third term in the integral, as you'll see hopefully in just a sec. So we're going to get minus kbt as before, and the limits we're going to have minus mu over kbt to 0. Now our density of states function is going to start off the same, but of course x is going to go to minus x, so we're going to get mu minus kbt x instead, and instead of this term we're simply going to swap this minus sign for a plus sign, 1 plus e to the x, and dx is going to become minus dx right there. So it's going to be a dx, and this is going to cancel with that minus sign right there. Now the integral between minus a number and 0, so say you have like a function right here of minus a number to 0 right there. So say that's our function. You can in fact just simply rewrite this, as long as you flip the sign, as the same thing as this integral right here. As long as you flip the sign of the limits and flip the sign of the function, you're doing a reflection in the x equals 0 axis. Then you can rewrite this as one and the same as minus kbt multiplied by the integral between 0 and mu over kbt times the same thing. So that is true of all functions. You've just basically mirrored it. You're evaluating the exact same thing under the curve right there. So e to the x minus 1. Now we're going to do a slight approximation right here. This is using the fact that we are in the low temperature regime, and we are going to be assuming that mu is a lot greater, or the modulus of mu is a lot greater than kBt, a bit like with the ideal gas approximation. And so for that, we're going to be assuming that the top limit in this integral is basically infinity right there. Now this might seem a little bit arbitrary, but you find that for small temperatures way less than the Fermi temperature, this approximation is valid. So let's go ahead and do that. So we're going to get minus kBt times the integral between 0 and infinity, rho of mu minus kBtx multiplied by 1 over 1 plus e to the x dx right there. So now this is looking a bit better. If we go back to our third term in this integral, we're not too far away, but we do have to do a little bit of work on this term right here. So we've done as much work as we can on n2, but for n3 we have to do a little bit more work just to get this in terms of x rather than in terms of epsilon. So again, we're going to make the same substitution, that epsilon minus mu over kBt is equal to x. So we've done n2, we're now on to n3, and we're just going to make the same substitution that we do again. So epsilon is equal to mu plus kBt times x, and d epsilon is equal to kBt times dx. So we're going to rescale this. When epsilon is equal to mu, we found this before, x is equal to 0. And when epsilon is equal to infinity, then we find that x is also equal to infinity. So when we take this to the far limit, it's going to be way more than sort of mu, and we're going to find that x is going to be equal to infinity. So again, redoing this density of states function, not in terms of epsilon, but in terms of x. This time, we're going to get rho of mu plus kBtx, which is actually what we had before, but then we made the transformation, and so hence we had this minus sign right here. And we're going to get 1 over 1 plus e to the x. And instead of the d epsilon, we're going to get a factor of kBt, which is going to come out the front, multiplied by dx right there. And now look at this. We have, after all this work, gotten the two kind of compensatory integrals looking very similar. So let's just highlight these two integrals. We've got n2 right here. That was one of them. And n3, we have them between the same limits and evaluated over the same variable. So what can we do? Well, we can just combine the two together, and there should be no problems whatsoever with doing that. So of course, that's kind of what we wanted to do anyway, and then we're going to just add this on to the first term, and then that will give us our total number of particles, our total area underneath this white curve right here, which is of course what we're trying to been doing for ages. So let's go ahead and add them together, and we are going to have a kBt out the front as a common factor right there, and we're going to have the integral again between 0 and infinity, because that's common to both integrals, 1 over e to the x plus 1, or 1 plus e to the x. I've just swapped the order for some reason. And the only two terms that are going to be slightly different are the two density of states terms. So we've got a plus rho of mu plus kBtx. And of course this is going to be subtracted, because of course we have this minus sign right here, rho of mu minus kBtx right there. So we've combined both these integrals into one integral, which is kind of, you can think of as the correction integral, to get the total number of particles away from absolute zero. Now, what we have to do is we have to sort out these two density of states terms. And the way in which we're going to do that is something that we've actually done a little bit before, is we're going to Taylor expand these density of states terms. And we're going to assume again that kBtx is a lot less than mu, and that's going to basically mean that we're going to take the first order of these Taylor expansion terms right there. So let's take out our density of states terms, and let's firstly do the plus one right here. So rho of mu plus kBt times x, we're Taylor expanding about rho equals mu. So this is going to be approximately equal to rho of mu. So that's going to be our kind of base term right there. And of course, with the Taylor expansion, we are going to have the derivative of rho with respect to, well, this whole variable, which is epsilon. This is, of course, rho of epsilon, but evaluated at epsilon equals mu, multiplied by the first sort of deviation term, kBt times x. So that's our kind of first order expansion. We're only going to go to that order. And of course, for the other one, we're going to get rho of mu minus kBt times x, which is of course rho of minus epsilon as well, is approximately equal to rho of mu. Now in this case, it's going to be exactly the same, only we're going to have a minus sign right here. So it's going to be minus d rho d epsilon, evaluated at epsilon equals mu, times kBt times x right there. So when we subtract these two terms, then you can kind of notice that this rho of mu is common to both terms, but it's just being added and subtracted again. So the only terms that are not going to cancel out is actually the second term in both expansions, because they have a different sign. So let's go ahead and just write in the second terms in this integral right here. And in fact, what I'm actually going to do is I'm just going to add on the term that we had before, which was just the amount of particles at temperature equals 0. So let's go ahead and just write the total number of particles in our system. And that is going to be 2/3, this is the bit we did before, times CV times mu to the 3/2. So that's just our bulk term. Most of the particles are in this term right here. But we still have this integral, so we're going to get plus kBt, and we're going to be integrating between 0 and infinity. Our Fermi distribution, instead of writing x, and our Fermi distribution, which is 1 over e to the x plus 1. And like I said, we're going to have these terms are going to cancel when we substitute them in, but we are going to get these two terms which are going to add because they have different signs and they're being subtracted in this integral right here. So let's go ahead and do that. We're going to get d rho d epsilon times ktx, kBt times x, and then we're going to plus again d rho d epsilon, both of which evaluated at mu times kBt times x dx right there. So we're going to have some common terms to both, which we can again factor out the front just to make our lives as easy as possible. So what we can see is kBt is common to both these terms and is also a constant right there. It's not in terms of x. And likewise, d rho d epsilon evaluated at mu is also common. So we can actually put all this out the front. So we're going to get d rho d epsilon evaluated at mu. Now we actually already have a kBt right there, so we're actually going to get kBt squared right there, and that inadvertently is actually the really important bit, but I'll just finish off the rest of this integral and then talk about this bit right there. We're going to get an integral between 0 and infinity, and what's left? Well, we got our x term, which is common to both, and it's being added, so it's going to be 2x divided by e to the x plus 1. All of this we have just got right there inside the integral. It's just a number. There is no nothing physical going on whatsoever in this integral. It is just going to be a number which is going to converge at high x, because of course we have an e to the minus infinity term, so we can actually tell that's going to converge, so no problems there. And this number, as it turns out, this integral between 0 and infinity of 2x over e to the x plus 1, this is just pi squared over 6. So that's an integral identity, a mathematical integral identity. It's literally just a number, pi squared over 6. So all we now really have to do is just sort this term out right here, which is a little bit vague. And it's literally just a derivative of rho with respect to epsilon evaluated at mu. So what do we say that rho was? Well, rho is the density of states, which is, of course, we've said many times, CV times the square root of epsilon. So if we simply differentiate that with respect to epsilon, then we are going to get, so again, simple derivative, we're going to get 1/2 CV times epsilon to the minus a half, which we can write as CV over 2 root epsilon. Of course, this is being evaluated at the chemical potential mu right there. So this is again equal to, so d rho d epsilon evaluated at mu is equal to CV over 2 root mu right there. So there we go. We have our term right there that we can substitute back into this n total right here. So we get, at long last, the total number of particles, and this is the final result, is 2/3 CV mu to the 3 over 2 plus this extra term right here. So this was the term we had before. This was the term at t equals 0. But now we have a temperature, we actually have an extra term right here. And this is where it comes from. And so this is going to be CV multiplied by, now this 2 is going to sort of multiply with this 6 to get 12. We're going to get pi squared over 12. And in fact, I'll just put all the number stuff at the front. Pi squared over 12 times CV times kBt all squared divided by the square root of the chemical potential. And this term right here, this term is called the Sommerfeld term, and this is what gives rise to the behavior that we observe within a metal. Specifically, this actually can tell us quite a lot about things like heat capacity and thermal conductivity about a metal right here. And this is where it comes from, because before, they didn't understand these phenomena that well. Thermal conductivity, electrical conductivity, and heat capacity, they did not understand historically using classical physics. But this result right here that we got, this result for the total number of particles, we got this by thinking a bit about the quantum effects and counting over densities of states. And we've actually obtained this temperature dependence of n. So we can see that for a constant chemical potential, if you keep the chemical potential fixed in a system and allow the total particle number to change, then you can see that as you increase the temperature, then more particles are going to flow into this gas right there. So let's just plot out what we've just derived right here. And we are going to see for a chemical potential, mu, for a fixed chemical potential mu, then the total number of particles in a gas, so this is T and this is going to be N, the total number of particles in a gas is going to increase sort of quadratically with temperature because it's proportional to T squared. So you're going to get a quadratic dependence of N on T. Conversely, if we consider the system where you actually have a fixed particle number and you adjust the temperature and then in effect the chemical potential changes, a bit like this kind of thermostat model, then if you plot the chemical potential as a function of temperature, then this will also change quadratically so as to conserve the number of particles right there. And of course, from this graph right here, you can see that if the temperature is large, then the chemical potential goes negative. You can see it's across the x-axis right here, or the t-axis right there. And you can see that it's going to go very, very, very large in magnitude, but very negative. So this is in, again, accordance with the dilute limit. T is large, then mu is much, much less than 0, and the magnitude of mu is much, much greater than kBt. So you can see that if the temperature is large, then the electron gas behaves pretty much like an ideal gas. So that was a very long video, I appreciate that, and that was quite a lot of advanced mathematics. I appreciate you probably didn't have to follow along with all the maths, just as long as you kind of maybe absorb some of the key points, and we got the final result for the total number of particles as a function of temperature and chemical potential right there. And the next video, we are going to be sort of finishing off our kind of view of fermions, and we're going to be talking about these things such as heat capacity, thermal conductivity, and electrical conductivity, and seeing how we can obtain these quite useful like physical properties as a result of this derivation that we've done right here. So I hope you guys enjoyed and hope that was informative, and see you guys in the next video.